Yes. Okay. Okay, so are we all ready? Yeah. Okay. Brace yourself. Okay, so is it? This paper is called Topology-Preserving Deep Image Segmentation. Just a bit of a background. Image segmentation is big doings in this field in particular. This lab has done some work. MGH and FreeSurfer are kind of the big names in the field. And FreeSurfer in particular has struggled with topological errors in image segmentation. And so topological preserving segmentation is something they would probably consider a gold standard. And it's something they actually are working towards with different methods other than this. But I'm going to start with the basics of what topology is, or rather topological data analysis. So just because I think most of us should be up to speed, but in case we're not, geometric topology, which is what we're concerned with here, is basically about components and holes in the components. So if you have a geometric object, how many holes are in the object? More generally, what that means is there a continuous deformation that can map one object to another? An example, I can scale an object, so I can take a sphere and scale it and make it bigger. Thus, that object is homeomorphic to the larger object. Homeomorphic means they're the same over this continuous deformation. The same meaning there is an inverse function. So in scaling, the inverse function is.
So in this continuous deformation, self-intersection are allowed or not?
Self-intersection, no.
What?
Is that your?
That was my question. You answered it. Thanks.
If you think of a continuous space, a disk, a sphere. Actually, no, this is too much in the weeds. We'll get into the actual meat of topological data analysis. So in things like images or data or anything digital, we don't really have a ground truth. I can hold up a sphere in 3D space, a physical sphere, and say like, oh, there's a hole in it, or there isn't. In data, it's much messier. We don't really know what a hole is or what a hole isn't. A good example is something like the mnist data set. So zeros in the mnist data set very clearly have a single hole and a single component, or at least they're supposed to. But most of our data isn't that cut and dry. And so that's where the field of topological data analysis comes in that it tries to estimate what that topological information is. And one of the most basic principles is how do you define this data? So whatever your data is, whether it's like a point cloud or image or a graph, nodes on a graph, whatever it is, you can cut it up into simplicial complexes. More generally, cell complexes. In a kind of canonical example, the simplicial complex, you cut your image or your node or your point cloud into sets of points, lines, and triangles. So in an image, actually, if you see the graph in this diagram, that is essentially what I'm talking about for an image, where each point is a pixel. Each line is a pair of pixels. Each triangle is 3 pixels next to each other. And there's many different implementations of this. You can have simplicial complexes, triangles. You can have cubical complexes. You can do something more abstract, like you see with this torus. That's probably from a RIPS complex. Because this is concerned with images, what they use. No, we're not actually. Okay. So when we understand the idea of these complexes, one thing that's important to know about these complexes is that if you have a triangle, this triangle is made up of faces. These faces are both the lines and the points within the triangle. And then you can extrapolate this to any other kind of complex, not just triangles. And this is actually a requirement. If you have a complex, a set of simplicials, all of the faces of a given simplicial need to be in that complex. Homology is how is in general, in very like abstract algebraic terms, it's a way to generalize associations between objects. In our case, for geometric objects, we're looking at how close two objects are. So if we take the example of an image, how close are 2 pixels? Well, obviously, if 2 pixels are next to each other, they're neighbors. Homology is how we kind of capture these components, these groupings of pixels or points, and the holes that are within these connected components. Does this make sense so far? Are there questions? Because I'm kind of racing through it because our knowledge base is kind of like very broad on this topic. But okay. Persistent homology is, well, I guess to back up a little bit, in data that is noisy or not binarized. This idea of simplicial complexes can be complicated. Like, what does it mean for an image to have gray values? In a binarized image, it's very clear, like your groupings of ones, that's a connected component, a space of zeros within a connected component, that's a whole. That's very obvious, but in noisy, gray, non-black and white images, it's different. And because of that aspect of data, that's why we need persistent homology, which is how these homological classes change over some concept of time. This concept of time is known as a filtration. So an example of this is in a point cloud. So we see this point cloud on the left, and we know that this is a circle, right? It's a disk with a hole in it. We can see that, but of course, how do you digitize that? And so if you, so you start at these points, and if you see the blue disk that's moving around these points, that's expanding, what they're doing is they have this filtration, which is the space around each yellow point based on the Euclidean distance around that point. So as you can see, as these blue circles kind of interact with each other or touch, you can see that some components are essentially being combined. When 2 components are combined, we refer to that as a death. Death. So so if you see here, and this is on the right side, this is a persistent diagram. So we start off at the birth and the death. So all of these points are birthed at Well, I guess one is burst at 0. They die when it touches another connected component. So I don't know. I think the diagrams like this GIF is a little self-explanatory. But you can see that blue dot at the very end, at the very end, that was the hole that we see.
It is an object too.
Yes, it's an object or a point, or they call it different things,
So
but
it has to
it's,
disappear. That's why it goes until the hole disappears.
yeah, yes, exactly. See, so as soon as the hole closes up, that's when we see that point die. And then we can see all the other points.
Yeah, they're always dead when it's a ring, right?
Yes. They, at this point, they are all dead except one. One is alive. When two components merge, we've essentially decided that one of them dies and one of them lives. The most persistent lives. So for this diagram, we would have one connected component that starts at 0. I guess. Yeah, at 0 point something, whatever the filtration starts at, it doesn't matter. And it persists the entire time, even after the hole closes up, because it's still one single connected component. It's just murdering all of the other connected components.
So the points in the very beginning are not the connected components.
Each point starts off as a connected component.
But in the very beginning, there is no birth of all of these points.
The filtration actually starts at like 0.1 or something, because Euclidean distance is 0. That doesn't make sense. Was that not your question?
I think her question was that whole big thing at the end, when does that burst? And I think it's just one of them that it's not, doesn't matter which one.
So you once it creates the dot, you can see. So this is it's burst at about 0.3. So when the Euclidean distance around each point is about 0.3. At that point, that's when we see this entire circle exists. And that's what creates the hole. And you can see it in this diagram as the birth. And of course, it dies at whatever 1, I guess. Does that answer your question?
No, I mean, on the left graph, we have points with non-zero size, but maybe actually, no, usually the signs of the point is 0. Does it make sense?
The size, they don't start the filtration at 0 because the Euclidean distance is 0. I don't think makes a lot of sense. And it might also be part of there. It looks like the filtration starts at about.
I think it's about language, point versus an object. You probably.
A point is an object. A point is an object.
Like it has
Point
the
is an
bulge.
object.
Yes. A point is an object. A point starts off as a connected component. So maybe we can consider that as erroneous language, but it is an object. And then as this point increases and merges with others, that's when we get the connected. That's when we get the components. Does that?
Actually, the components grow larger. When it merges with some other component, the component becomes one and it grows.
Yeah, I mean, each component is growing, whether it's touching other components. But yeah,
Similar to connected components in a graph, right?
yes. So, and actually, you can also talk about this. There is graph topology, which it's essentially very similar, where instead of Euclidean distance, you're filtrating over the weight values. And so if you have a fully connected graph, well, at the end of your filtration, you have one connected component, which is your entire graph. So yes. Okay. So barcodes are just like a fancy way to describe these persistent diagrams. So this is an example where I believe we start off, so in the top left, that square of points and little connected components. That is our starting position. And there, I think there's about 10 of those objects. And we can see as our filtration grows, which is these squares. These objects are dying. And we can see that in the H0. So H0 is our little name for objects, connected components. H1 is the fancy little name for holes.
Isn't it expensive to detect holes?
Not now, well,
Because it's a relationship between objects and then at least quadratic you have to
yeah,
consider.
oh, it's
Blah,
quadratic.
blah, blah.
It's quadratic. It's basically the same as cycle detection.
Okay, so you're treating everything as a graph.
You know, but it's the same concept. So you don't need to treat it like a graph, but it's the same concept, basically same runtime.
Mhm.
But what other different colors?
Those are when the those are the different sizes, the yellow is triangles, green is squares, blue is something with 6 sides, red is 5 sides. So it's the number of sides in this, I don't know, the size or the type of object, the type of object. Triangles, squares, blah, blah, blah.
Can you just call it the nth order homology or something?
What?
Say it again.
So you can just call it the nth order homology.
Yeah, so if you're talking about the homological classes, I can refer to them as H0, H1, etc., or the homological classes. I'm trying to use more generalized language or conversational, but we're gonna watch a video. It's only 25 minutes. You don't have
sure?
to. Yes,
Are you sure you're playing the video right now?
you can't see my screen?
I mean, do you want us to watch the video right now?
No.
Yeah, let's do it. Are you skip ad now? But will we hear anything?
No, you don't need to.
Full screen sometimes works better. Double click. Or full screen, the rightmost, yay.
Okay, so we're gonna talk about cubical complexes. So we talked about simplicial complexes, which are triangles. We can, you know, there's all sorts of ways to abstract it. You have the same kind of idea in graphs. We're gonna talk about cubes. So cubes are, of course, points, edges, squares, and cubes. And this, so the reason I'm showing this video is because this guy, just the slides themselves describe cubical complexes really, really well. So he takes this data set, mnist, which, as I mentioned, and he specifically takes the 0 because it's very clear. He inverts the image, so you know, darker pixels are now sorry.
Non-object.
Yeah.
The pixels are non-object pixels.
Yeah, and he just inverts the color, so you can filtrate from 0 pixel value to 1, I guess the max is 15. So if before we talked about the filtration over Euclidean distance, this time we're talking about filtration over pixel value. So. Okay. So if we saw that matrix of numbers as a representation of MNIST, we can see how we build the faces over our filtration. So if our filtration starts at value 0 and works upwards, we can see that, you know, here at a filtration value of 3, we have these connected components. So 3 of them are just kind of sparse pixels with no neighbors. And we can see the barcode down at the bottom. So as we filtrate higher, the barcode becomes more interesting. We can see how all of these things die. So if you see the blue lines, we can see all of them die at this filtration of 7. This is when the whole thing becomes one connected component. And we also see when the squares come in, the square complexes come in. So as the filtration grows, we're always finding when these faces, the lines, the points, and the squares begin and when they die, when they touch other components.
How do you decide to go with the square instead of triangle?
So you can do both, whatever your data is, you can do either. This paper, which this paper uses cubical complexes. You'll have to ask them why. If you look at an image, you can kind of clearly see that squares exist in the image, that if you have 4 neighboring pixels, it makes sense that you can view this thing as a grid or a set of squares or a set of cubes. But of course, you can also do triangles. So it's up to you what you want. I think the biggest difference is resolution. For every square.
Can I add something here?
Yeah.
Hi. So what I wanted to say is that whether you choose to use triangles or cubes, you are going to end up with the same number of connected components at a certain level of filtration, which is 1 in this case. You're gonna, whether you choose to use triangles or squares or cubes, you are going to get a 0, an object of the shape of 0 at some point, which is one of the things that Damiano does mention in this video as well. So
yes, yeah. In this case, both. Yeah, sounds exactly right.
And the reason why we use cubes, we choose to use cubes or square in this case, is because the real world data, like the images here, it's just they're all arranged in a grid, so it makes sense to use squares here. If we are working with 3D data like brain images, the data is arranged in a 3D grid, so it makes sense to use cubes over there. So
I would argue that triangles also make sense. Triangulation is a big deal. Like it's
yeah, it does. It does make sense, and the point is that you are going to arrive at the same conclusion no matter which complex you choose. So
yeah, the only difference is resolution.
Yeah.
Whether you have 1 square or 2 triangles, and you'll get the same results, especially in this case, this example. I assume there are corner cases, but it doesn't matter. It's a little bit of personal preference. So, because Pre-Surfer uses triangulation. But anyway, I think that. We can also see in dimension 1, the holes H1. When the actual hole begins. It begins at filtration value of 10 And then at 15, the whole thing is now closed up. So that should pretty much explain.
So it's 10 and Euclidean distance.
It's not Euclidean distance, it's over pixel value. That's what we're filtrating over. I was talking about Euclidean distance because I think it's a good example. However, it might be kind of misleading. The idea of topology is there is no one set implementation of filtration. That's why topology can be applied to, that's why you can have the topology of a graph, the topology of an object, the topology of an image. It's all very generalized. And then the implementations are data specific. So if I had a point cloud, I would use Euclidean distance. If I had an image, I would use a filtration over the pixel value. So. How do I? Okay, go back to the slideshow.
Yeah, you looking for?
Okay, now we're gonna talk about the page. So they basically took this idea and applied it to image segmentation. In their case, it's neuron maps. But you can do white matter segmentation, whatever, blah, blah, blah. This idea has already been done. Their big contribution is that they did it for segmentation. And they used a different loss function than what has been used previously. But we'll talk about that later. So in segmentation, you have some kind of, in a trainable segmentation model, you have some kind of ground truth, which is an already created segmentation map, and then your input, which would be just this. In this case, it's just an image of neurons. You can also use the case of MRIs. They have two loss functions. One is the normal reconstruction, construction error, which is how well does it perfectly construct the segmentation map. And the other is a topological loss, topological error. So this topological error defines the distance between the topological information of the ground truth and the topological information of the prediction, the predicted map. So what they do is they build persistence diagrams for both the predicted likelihood map and the ground truth. And from those persistent diagram, they use the Watertine or Earth. Oh, right. Sorry. There's another slide I forgot about. Their filtration is over logics. So we've been talking about pixel values. Well, because their predicted maps are logics, their likelihood maps, our filtration goes from 1 to 0. So that should kind of clear up some of the implementation details.
Quick question, do you know how long it takes to draw those maps? Like, isn't it too expensive to compute for like in training, if you want to train with thousands of images?
Or I'll put it this way, we couldn't have done this in 1980. But we have the hardware to take care of that. It's no more intensive than neural networks. It's not anywhere intensive as something like a large language model. But you're right, it is, I think it comes down to quadratic time, so it can be kind of expensive. It's not something you can do with low-end hardware. So their loss function is this Wasserstein distance or the earth mover distance between the two persistence diagrams. So this, most of this should be kind of intuitive, that we have the birth of a point. So a point can be a whole or a connected component or whatever. So you can see that you have the birth of a given point minus the birth of the same given point in the ground truth image. And then the death of a point minus the death of the same point in the ground truth image. So that's a little hand waving. What does it mean for two components to be matched? Well, that's what gamma is. Gamma is a matching function between a component in the predicted output map and the ground truth image. So ideally, you would have a perfect match. You would know what component in the map is supposed to be the component in the component in the prediction is supposed to be where it's supposed to be in the ground truth. But of course, nothing's perfect, and this is actually all hand-wavy nonsense to say we take all the components, all the holes of the predicted map and the ground truth, sort them by how persistent they are, and then that gives us our matching. I think that kind of matching is a little hacky, but it gets the job done. So, and we're engineers. Hopefully, does that make sense? Because that's actually an important caveat here. It's one of the flaws in TDA and possibly one of the strengths. So if there are questions about the matching, ask them now.
How do you know the ground truth?
So you have the ground truth images, which would be already created segmentation maps. Actually, that's good to know. Hold on, sorry. There's a, okay. So this top barcode is our ground truth. Our ground truth is a binarized segmentation map. So if you notice how the persistence is, it's always perfect. It's always from 1 to 0. And that's because they're binarized maps. So I won't lead into that now. And that note is important later on for one of their metrics. But part of their methodology is now it's questionable why they did this, but I actually think it's kind of cool. So they had these images of neuron maps, or they could be MRI slices. Oh, by the way, just to be clear, this paper was all for 2D images, but you can extend it to 3D. Anyway, they are not just concerned with global topology. As an example, if you take an image and flip it, it's going to have this exact same topological information. But you flip the image, it's not actually what you want. You want something that the way they describe it, they want to preserve local topology. And so that's why they cut the images up into patches. So I think there's 64 by 64 pixels, patches of the image, and compute and train their model on these localized pieces. I think there's a strong case to be made that in our kind of data with images, we actually do care about the topological information in a localized way rather than just a global way. Okay, so they cut them up into patches, trained their model using the loss function we saw, plus the construction error. And that's essentially how the model trains. Okay. Cool. Before we get into the evaluations, is there anything that didn't make sense about the paper? Is there anything anybody didn't get? Is there anything anybody didn't like? So this is all well and good. Oh, actually, there's a caveat. The Wasserstein distance is done on distributions, right? And so it may not actually be intuitive on barcodes and persistent diagrams. Well, the thing is these persistent diagrams, when matched or ordered correctly, are a distribution. They're a distribution where the y-axis is the persistence value or the birth or death, whatever, with the persistent value rather. And the x-axis is the component, the list of components. And when ordered, when matched, that, for me at least, that actually makes it an intuitive relationship between these persistent diagram and the actual Wasserstein distance as we consider it.
So complicated.
Is it? What's
No, I'm just. But what about, so it trains on the input image and on the segmentation. But in addition to being encouraged to produce correct segmentation, we're under this topological constraints or regularizer. It also is doing reconstruction.
yeah. So the loss BCE, I don't know what BCE stands for. That's construction error. That's how well is it constructing the ground truth segmentation map.
Oh, so it's not, it is segmentation. It's not an autoencoder that tries to reconstruct the input.
Correct.
It is
Yeah.
not.
Yeah. I tried to make the language clear that it's construction, not reconstruction. It's not trying to reconstruct itself. It's constructing the segmentation map.
And in what kind of space do we calculate the Wasserstein distance?
It's over the persistence diagrams. So your persistence diagrams are basically this list of your objects, your H0s and your H1s, and how persistent they are.
So like in the lower figure, am I right?
Yes, those are the persistence diagrams, and it might make more sense to see them as a distribution when we look at the barcode. So the barcodes, I think, are actually kind of visually, you can kind of connect the dots between that and a distribution.
Yeah.
Does that? So this is all well and good. How do we know they're right? We don't.
Wait, you said they have ground truth segmentation.
I'm trying to be cute to lead into the last slide. This is slow. All right. So they did different evaluations on this stuff because, okay, great, we have reduced the topological error, but does that actually mean our maps are better or they actually do preserve the topological information? And so they evaluated it with 3 different metrics. I'm going to talk mostly about something called Betty numbers. A Betty number is for each dimension, H0 over H1, how many objects are there? How many components are there? How many holes are there? And the Betty number is defined per dimension. As the kind of canonical example in MNIST, the H0 Betty number is 1 and the H1 Betty number is 1 because there's one object, one component, and one hole. And so you can compute that on these segmentation maps after binarizing segmentation maps. So you take your predicted output, you binarize them, and because they're logits, that's actually intuitive, right? You just cut them off at the 0.5 mark. But then you compute the Betty numbers for each dimension of your predicted, and you find the distance, the errors, the difference, between that and the Betty numbers in the ground truth. And what they say is that without the topological loss correction, the Betty number error is worse, that their loss function. But that, I mean, that seems obvious, right? It actually seems. So even though I think it's a valid metric, it would be strange if it failed that metric. It didn't improve. They used two other metrics, which I think, I don't know, they just seemed less useful. They were about clustering what they consider the foreground or the actual segments, and then matching or comparing those clusters from the predicted map to the clusters in the ground truth. But I don't know, I think the paper is interesting. It came out like almost at the exact same time as a paper by a different lab that does a similar thing with a different loss function that we've actually talked about here in this group before. And so I don't know that it adds much because, and also to back up a little bit, the Wasserstein distance over persistent diagram, that's like 10 years old. We've considered that as a distance or a loss function for 10 years. So that I would not consider that to be a novelty. I think what is important is that they actually looked at segmentation through this perspective. And I think the patching is kind of cool. I think that's a cool idea to look at localized topological information in this setting. I think we're kind of out of time. I raced through some stuff. There's a lot of complexity that I didn't talk about. We can talk more about topology, or we can dismiss the class.
So finally, what do they optimize to train?
The loss, so the actual loss function. Jesus. That's the actual loss function. In the little red rectangle, LBC plus L topo. And there are two loss terms. The LBC is the construction error, like how well is it constructing the segmentation map, and then the L topo is the topological loss term, which is this guy, the Wasserstein distance.
So here we can optimize the gamma function.
So the gamma function isn't necessarily optimized. What it's optimizing for is that segmentation construction. That gamma function doesn't, the gamma function itself, the idea of the gamma function doesn't change. It's just sorting the components. So you just sort the components, and that's how you match them.
Or it is searching over the possible gamma functions.
No.
The equation says that find the gamma function that minimizes the loss. Is it?
So yes, but that's only because the sorting changes.
Mhm.
So all the gamma function is a sorting, but as you're changing the persistence indirectly by changing the actual size or shape or connectedness of the segments, that's how you're changing the persistence, which changes the sort order. So you're optimizing for that sort order.
So the capital gamma is actually set of different orders.
Yes, it's all possible orders.
That. I guess that's it. Is this published somewhere?
Yeah, it's published in 2019 in NeurIPS.
Yeah, that's interesting, but what do you think yourself? Isn't it like overcomplication, or is it more like, is it needed, or?
I would say it's useful. FreeSurfer and Bruce Fischel obviously and clearly have struggled with, and maybe struggle is not the right word, but they've noticed that you can get topological artifacts, and they've been doing all this research to kind of correct it. And as TDA has really like kind of exploded in the last decade,
What is?
topological data analysis.
Mm.
I think it does have a place in this field. I think it is useful. I would also argue that it makes our models more sound. So I would argue that any kind of regularization makes our models maybe more interpretable or more meaningful. Any kind of constraint on a model or a prediction can tell us more about that prediction or that model.
Interesting. So you're saying if we know the objective function of the model, this is kind of what it optimizes for, then that means it's more predictable. Or no, interpretable. We trust the model more.
Yes,
So if I know that your objective function is to minimize your involvement, then I kind of trust, okay, well, I can rely on Noah to be unreliable.
that is the most perfect example I've ever heard. Yes,
Like, so really, you think if we know what the thing is optimizing,
Mhm.
then that means trust. Trust is knowing what objective the other party is optimizing. I'm trying to
yeah,
tweak it, right?
no, that's
Compress
perfectly it. And as we constrict that error, what it's optimizing for, we know more about it. We have a smaller space.
The fewer things it optimizes. No, the more it
That's what
optimizes.
When I say
The more constraints.
Yeah,
The more it optimizes. Because
Yes.
everything that you optimize for constrains the space more and more and more.
exactly, exactly. The more terms you have, the more constricted your loss space is.
Interesting. Everyone agrees with that definition of trust?
I mean, yeah, if there's a disagreement with that, please.
Online people, do you want to comment on trust?
Not right now.
Was that?
No, not right now.
Not right now. Okay, no one wants to argue with you. No, we trust you because of we know your constraints.
My optimization functions all over the place.
For example, what are we optimizing right now during this? Lecture?
For me, my optimization is to get as close to 1 o'clock as I can. That's my optimization.
Asymptotically, no, like we still have 6 minutes.
I know, that's why I'm trying to drag it out.
Yeah, okay.
Okay, one more question.
Yes.
Uh,
See, I'm training them on.
do people use this method just for images and for videos, something like that, or can it be used for something else, for some abstract thing? I don't know,
Absolutely.
for text.
So, okay, this is why topology is most interesting to me. It's because it's the biggest, most generalized thing in mathematics, or one of the most generalized things in mathematics. Topological space is defined as a set of objects and something that defines closeness. At its most generalized, closeness is undefined. In geometry, closeness is, in Euclidean geometry, closeness is defined by Euclidean distance. In graphs, that distance can be defined as the weights between nodes. In images, that closeness can be considered the pixel value compared to its neighbors. And so anything that can define closeness, you can look at the persistence of that. And so for any kind of set of data, point clouds, graphs, images, 3D images, anything, any kind of abstraction you can consider, if you can define a closeness to that, a closeness that makes sense, then this is a method that will work for it. Gunnar Carlson has kind of written a book on this, and so he has a lot of examples. He's written a lot of details. He's covered a lot of different types of data. He wrote a paper which was basically this, but with a different loss function that really generalizes to different kinds of data. So yes, I think it's actually very useful across all forms of data. You just have to implement it differently. You have to consider the problem differently. What kind of complex do you want? That.
But do you think this like experiments on this paper is just them basically trying to do some like kind of edge detector in some sense? Because when you because when you try to segment brain like on 100 like regions, you don't have like any edges. Like the atlas came not just from like kind of edges, like because there's only like that set that has like edges, like retina or cells or
I mean, it is not the same information as edge detection.
No, I understand, but I'm just saying that like the approach is like, okay, we can find this kind of edges that like create a contour. So we matching basically prediction to the contour instead of like saying density prediction in some sense. So it's like regularization, you have a contour and you're trying to
It
contour.
is absolutely a regularization term.
Yeah, but I'm just saying
So
that like the like that's
it's not
support
really
the idea, but like if you go to atlas segmentation where you have like 100 classes, that atlas is not like they have like bunch of atlases and they will not overlap, for example.
so.
And you actually don't see any like kind of sequence.
Let's say your segmentation is, and I'll give an example to kind of answer this. Is just a single square, right? Then you have another image that is a single circle, a single disk. You're going to get the same loss between those two images with the Wasserstein distance over the persistences. In edge detection, you won't. So even though you can find more edge information from these topologically preserved images, it isn't just specifically about edges, because your topological information does not care about space.
I understand. I'm just trying to say that the simplest example will be like edges, or like some like example we have this blood vessels, right? It's easy to segment them out in the same show, like in roads on the map, it's easier. But like I know the topological part just says, oh, we can find these edges, we can find this kind of points that we can attach to and regularize based on this. Because we know that these points probably has some like topological sense, like edges.
Sorry to harp on it. Edges don't define topological information.
I mean, you can define it and maximize this topological metric distance and regularize this way. Basically what it does, like you have some prediction from the neural network. And you have, for example, buckets, right? And I put this bucket specific way, right? And then you say, oh, maximize your prediction from neural network to this bucket to make this shape. So this is how it regularizes. And this is like, if you change bucket, for example, you have other bucket.
So
It's just like alignment in some sense.
But cross the tipping point, now you're moving away from your optimal. As
I know,
close to one,
I'm over.
you're getting
Uh,
away from one.
But this might be valid. So. This is the thing about topographic versus topological information. Topographic information is really concerned with contours and edges. And wait,
Say examples like this.
yeah, and so if you perfectly capture your topographic information, then you have inadvertently captured your topological information. But if you preserve the topological information, there's absolutely no guarantee that you've captured edge contour information.
I understand. I'm just saying that in application, it will be like contours or something.
I don't think so.
Like, I'm just in the sense like, what like topological is nice about, it's you can have like some priors on your data, and then you add regularization to the geometry. Instead of like finding this geometry, that is usually much harder.
Maybe let's talk offline.
Like simple example, you training like ImageNet model, right? And your labels such as like uniformity. If you go like in wild case scenario where you have like long tail distribution, your models won't work as if like on ImageNet, because ImageNet has like uniform label distribution. So to make your model work on like long tail distribution, you can add regularization to long tail distribution. And this is like where your topological geometrical thing will come.
So if you have a ground truth image, which is just a square, and you put a hole in it, and then you take the same square and you cut out like a hole from the edge, right? So the topographic or something like the MSE difference will be the same for these two images between the square, right? But the topological loss will be inherently different. Topological loss between this and this is 0. Topological error between this and this is more than 0.
No, I have to give that other talk I was talking about.
And so it's not really just about the topographic information, contours, edges. It's not even really about the geometry of it. It's prioritizing this kind of error over this kind of error. So I don't think, I mean, I don't know, is that your position? Is that your argument?
No, I'm just trying to say is that like basically what's the trying to do, like in the loss function, you find some critical points that might follow some geometry, it's kind of prior knowledge. And this is how you utilize your kind of regular, maybe supervised or any kind of regular, like supervised learning, for example, with this topological information. So basically you improving your metrics with respect to some prior. And this is how you utilize. So this helps you to maybe converge faster or something.
It is absolutely a regularizer.
Yeah, I'm just saying this is how like topology geometry based like approach will help us. For example, there is a like neuroscience research that has like dynamics that have attractor points. You can use this attractor points, take this, I don't know, there are tons of estimators, but you can take space sign distance. And because it's discrete, like you have attractors are discrete, so you want to regularize to your attractors. So you can find like some, maybe you probably have like algorithms that can find this prior information, and then you have this like generalize any kind of supervised learning without like regularization. You add this regularization to this, and you supervise it to converge to your kind of solution.
And I would say that's true for pretty much any kind of regularization. Geometric topological L2, L1, it is always constraining your loss and hopefully moving you towards either better or more importantly, different error.
But I just want to like summarize it, because the experiment like very limited, like finding pi is really actually hard. So if you have algorithm to find pi, then of course it will help, because you strictly constraining your functional space of like solutions that the neural network can find.
Yeah, so in segmentation modeling, you're assuming that your ground truth is correct. And so, because your prior comes from that ground truth image.
I understand, but for example, like for near imaging, like for us, what will be prior?
Free surfer maps.
But then why you need like topology there?
Well, that's actually, I would say, the downfall of the
Okay, so
image segmentation.
maybe you can do something, you just have this dense prediction plus you compute contours.
Well, so, but no matter what, okay, there's. Let's talk, come to my cubicle after this, I want to show you a paper. Are there other questions? Okay. Oh, there were chats.
Thank you so much. It's fascinating, this resemble.
I just wanted you to generalize it.
Oh, no, thank you, let's. Okay, goodbye.